Hi, my name is Wayne Landis. We're going to talk today about putting together contributions of microplastics and other stressors in order to do adaptive management in California water, specifically the San Francisco Bay and the upper San Francisco estuary. I'm the speaker. I've had lots of helps, undergrads, graduate students, work study. And we have collaborators at the San Francisco Estuary Institute, Oregon State University. We're funded by NSF and several other state agencies within California. Our method has been published. I'm going to try something dramatic here. I'm not going to give background on Bayesian networks. There are many other papers on that. Just remember there are nodes. The interactions in the nodes are controlled by a conditional probability table. And the entire thing's probabilistic and it is a great tool. Here are the papers you should look at. It's all based on a real simple idea. We have a cause and effect pathway. It starts with sources, produce stressors that are in particular habitats or locations that generate effects upon the organisms or other features that are managed are considered endpoints, and that collection of all those different kinds of effects are the impacts. And the history and so forth is covered in Landis 2021. Here's our conceptual model. This is the one we started off with, actually, with the our studies on the upper San Francisco estuary. We have a variety of sources, a number of different stressors, water quality parameters, organophosphates, metals, and so forth. A variety of habitats for the kinds of species that we'd be investigating. A number of different kinds of effects. A lot of these are looking at community effects and also direct mortality to the endpoints. And we have large numbers of aspects of that system that are of interest. In the case fisheries, macroenvironment, community structure, water quality parameters, and so on. So this is how we set it up. Our data set is a combination of seed and surf data sets that's been collected in California for a long time, along with the San Francisco Estuary Institute, which has been looking at microplastics in the region as well. This is a little simpler way of presenting this. Just looking at land use, you can see the kinds of things that can come from different land uses, water quality, different kinds of pesticides can affect water quality, the toxicity, the kinds of habitats that things live in. And in this case, we make them very specific to the organism, the kinds of effects that can be generated and the various kinds of impacts and the impacts that can be generated to aspects of the system that people have an interest in. And this is often set by regulation. We've done this lots. This is a paper by Mitchell et al. 2021, where we actually look at different kinds of pathways. The green here is the organophosphate, mostly the organophosphates here in this particular case. They're working on acetylcholinesterase activity and depressing it. The blue are water quality parameters, which again can have effects. The yellow are the kinds of effects that occur as these materials go through and organisms are exposed to it. In this particular case, we're just looking at one organism or one endpoint, and that's Chinook salmon populations and the Yakima River. It was actually a meta-population. So this is the fundamental structure of our Bayesian networks, and it's been consistently this way for a long time. Here's another one for micro and nanoplastics. This is one of the first iterations from my student, Emma Sharp, who I believe is talking also in this session. Where again, you have sources, the kinds of stressors we're looking at, micro and nanoplastics, tire wear particles, which can be both, depending upon the tire and its wear and so on. We're looking at water column in particular. The effects can be acute, chronic, typical kinds of things you see in environmental toxicology, both at an organismal, community, and system scale, and the kinds of things that are being managed or example specific herring, oysters, anchovy, also human well-being, both for human health, but also the exploitation or use of that resource. Here's just one of the early conceptual models of how these pathways would fit together, from stormwater and wastewater effluent as being sources of these particles. You have the fish being concentrated in the fish, and the bivalves, toxicity, and then the different endpoints once again. So we have like a pesticide herbicide pathway here, water quality inputs. We're not going to talk about that for the rest of the talk. We're going to be focusing also on the micro and nano. So what we've been working on is building the tools so we can look at the pesticides, the classic toxic compounds, along with the micro and nanoplastics. This is our technical contaminant pathway, specifically drawn for the upper San Francisco Bay Estuary. Eventually, we're going to be talking about delta smelt, not at this part of CTAC, but eventually. We have the risk regions, the different parts where they're broken up within the area that we're studying. And these concentrations here from the malathion and so forth are actually derived from sampling. These concentrations depress or change the acetylcholinesterase activity by a certain amount, and that gives rise to mortality from that mixture. These data, the conditional probability tables, are based on the data of Kathy Letts from 2009. So this is an acetylcholinesterase pathway. This is a little bit different. It doesn't have a particular pathway. It's just the concentrations, the dose response that give rise to this kind of mortality. And then we have an endpoint here we're calling for now total fish mortality. The conditional probability table, again, see our other papers, in this case, are generated by looking at the mixtures and using what Eric Lawrence calls our dose response model averaging tool. So what we're doing is averaging these dose response curves, and I have shown examples in the past, and to generate this conditional probability table. That table determines the interactions of how two nodes generate an output node. So in this particular case, we just focus on what we call the confluence risk region. We have these concentrations of the various pesticides, and you actually generate a 71% probability of fish mortality being equal or greater than an EC20. So we're saying in this case, the EC20 would be like the threshold, the regulatory threshold. In this particular case, you have a fairly high probability of mortality being greater than that. When you do the sensitivity analysis on this, it's the bifenthrin is contributing more to this estimate than the other nodes. Emma's work again, this is the microplastics. In the San Francisco Bay, we have 4 risk regions. We actually incorporate treatments of the water when it's appropriate, and the seasons. California really has 2 seasons. Was it dry, 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 violently wet, dry again? We have the microplastic data set on exposure generated by the San Francisco Estuary Institute. And then the toxicity data here is actually generated by Oregon State and our collaborators there. Same basic process, different arrows, different materials, but again, we're going from the source, the amounts of materials, and their effects. And this is just, again, if you just want to see what risk is in the San Francisco Bay region, this is the numbers that were found, the treatments, the stormwater particles, and 3 different endpoints here, silversides, daphnia, and zebrafish, looking at what the effects would be. And in this case, it's the silversides that apparently are at more risk than the other 2 endpoints. You can actually just put San Francisco Bay, that particular part of the San Francisco Bay region study area, and you can generate very specific estimates, not just the entire area. So it looks like we can now look at these things where we have risk regions, a pesticide pathway, a micro and nanoplastics pathway, look at fish and vermin community structure and water quality. Now we need to look and see how we can build and parameterize these two models, allow them to work together, probably through some kind of model averaging. We have pretty good idea that this will work from our experience. We have lots of uncertainties that we need to look at, and that will be some of the interesting part. Come back to CTAC North America, hopefully in person next year. And if you want to see this video and other videos, just go to our Eco Risk Projects channel. And here's some other presentations being presented from our lab at this particular CTAC. Thank you very much.